Okay, in this class, we will discuss on basic operation of a new type of transistor called MOSFET, MOSFET. Okay, first, let's consider a device structure that made from metal oxide semiconductor. So this structure called MOS structure or MOS, because it is made from the metal layers, and then uh, at the below than the metal layer we have the oxide layer. So oxide layer is actually the material of insulator. So example of oxide layer is silicon dioxide. Okay, and then at the bottom layers is a p-type, is a silicon semiconductor substrate. So it can be a p-type substrate or it can be n-type substrate, and it can be any type of semiconductor. But mainly in our course we will focus on silicon devices. So we consider a silicon substrate. Okay. First, let's consider a p-type silicon substrate. Okay. This MOS structure actually form a capacitor-like structure. Okay. So this is the question. What happens if positive voltage is applied at the metal and substrate is grounded at the same time? So we want to consider what will happen when we apply the positive voltage. So means that here we have the metal, we apply a positive voltage. So we apply a positive voltage here, and then we ground the substrate. Let's say we put it, this is a voltage, so I put it V metal. Okay, when we apply a positive voltage here, this is positive. So what will happen? The oxide layer here will become a separator or isolator. It works as a medium in the capacitor. So we have here the positive potential at the metal, and then due to the physics law, so we can expect a negative charge at the substrate, at the semiconductor substrate, to pair with the positive potential at the metal. So what will happen is we know that the p-type semiconductor substrate, it has a many hole carrier. So hole carrier is a positive charge, and at the same time the p-type substrate has less electron, negatively charged particle. So electron is a minority charge of p-type semiconductor substrate. How if we apply a positive voltage at the metal, this minority electron carrier will be attracted towards the insulator. So what will happen is we can expect a formation of electron. Electron will accumulate at the interface of oxide and silicon semiconductor substrate. So this is what can be expected if we apply a positive voltage at the metal. Okay, so next we add an n-type semiconductor at the left and right side of the p-type semiconductor, and then we add electrode. This is electrode here. So this is the electrode to enable the voltage application. Okay, So this is the structure of a FET MOSFET. Okay, if the voltage is applied between the two N-type semiconductor, is there any current flow? Okay, let's say we apply voltage across these two electrode. Okay, so apply, let's say this is the V, I put the V2. Okay, V2. If we apply a positive voltage between the electrode number 2 with respect to the electrode number 1, the V21, so is there any current flow? Will there any current flow? This is the question. The answer is there will be no current flow through this first electrode to the second electrode. The reason is because of we have the N-type, P-type, N-type. This is this form of what we call NPN structure. So NPN structure. So this is the positive voltage supplied at the N-type semiconductor. So obviously this is a reverse bias. So the answer is no current flow. So how we can enable the current flow? How we can make the current flow from the electrode number 1 to electrode number 2 or vice versa? Okay. So next, we apply voltage between the two N-type semiconductor. Let's say we apply a voltage. This is electrode number 1, electrode number 2. This is V21. We apply positive voltage between two N-type semiconductors, and at the same time we apply a positive this is voltage is applied at the middle metal. So at the same time we apply a positive voltage at the metal. So this is a V metal. So what happened? Will there any current flow between the electrode number 1 to electrode number 2 or electrode number 2 to electrode number 1? So the answer is yes. The reason is when we apply a positive voltage at the metal, so what will happen is we attract electron, the minority carrier inside the p-type towards the oxide layer. So what will happen? There is a accumulation of electron at the oxide interface. So electron will be accumulated, and this very thin accumulated electron channel will bridge or will connect this electrode number 1 to electrode number 2. So the current from the electrode number 1 to electrode number 2, for this application V21, so the current is from electrode number 2 to electrode number 1. So the current can flow from the electrode number 2 towards the electrode number 1 via the formed electron channel inside the p-type semiconductor. So this is what we call it a channel, the formed channel due to the application of positive voltage at the metal. So this in general, in summary, this is the basic operation of a MOSFET. So we are using the MOS structure in order to control the on and off operation of a transistor. Okay. The structure that have been described in the previous slide is called a MOSFET, and this is called a type enhancement type or EMOSFET. Okay, for the EMOSFET, there is no physical channel built in. There is no physical channel built in. Okay, so means that between the source and the drain and the source, there is no physical channel because the N-type at the drain and N-type at the source is separated by the P-type substrate. So there is no connection, physical connection. So EMOSFET is normally off. Okay, so without any application of voltage at the gate, EMOSFET is off. There is no current flow. So we need to apply a positive gate voltage to induce or to enhance the channel. So when you apply, for example, this is a P-type substrate, we need to apply a positive voltage at the gate. So this is when we apply the positive voltage at this terminal. So what will happen? A channel, electron channel will be induced or will be enhanced. Okay, before that, I forgot to mention about the naming of the terminals. So if you compare with the structure that shown in the previous slide, we have the middle metal and we have the electrode number 1, electrode number 2. So electrode number 1 and electrode number 2 is referring to the drain and what we call it what we call as a drain and the source electrode of a transistor of the MOSFET. So we have drain and source. So drain and source is the two electrode that where we apply the voltage and we measure the output current of the transistor. And then the middle gate electrode is called gate electrode. So gate electrode is the electrode that control the conductivity or current flow from drain to the source. Okay. So we see here, this is enhancement MOSFET because we need to apply voltage to enhance, to induce the electron channel, okay, in order to obtain the electric conductivity between source and the drain. Okay, so but however, we cannot simply assume that if we apply any positive voltage, the channel cap will be formed. This is not the case. We need to apply a positive voltage in case of this P-type substrate that greater or higher than a voltage, a value called threshold voltage. So there is a threshold voltage. So below than this threshold voltage, there is no channel formation, but above the threshold voltage, the channel will form and the current can flow from drain to the source. Okay, this term threshold voltage is denoted as a VTH or sometimes as a VT, sometimes VGTH, sometimes VGSTH. So the representation of threshold voltage may differ from one reference to one reference. And in fact, in our learning material, sometimes I may use different symbol or different representation of the threshold voltage. So please take note on this. Okay, the next slide discuss again about the operation. So the first statement here, the positive gate voltage pressure. So there is no physical without any positive voltage application at the gate. There is no physical. There is no channel. So this is a induced channel. So induced channel is due to the positive gate voltage. For positive gate voltage, pressure the hole to leave the area. So because the substrate is the p-type substrate, there is many holes. Majority carrier is hole. So hole will be pushed away from this from the interface of the insulator, because hole is positive charge. So repel, and then there will be a extension of depletion region. Okay, and at the same time, the positive gate voltage also attract the minority electron from the substrate to the interface, insulator interface. Okay, if the gate is made sufficiently positive, so the word is sufficiently positive, enough for the electron to be pulled up from the substrate and accumulate in the region near the surface of silicon dioxide layer. So this is the time, or this is the time where the induced channel is formed. So the induced channel will connect the drain and the source, so it result in the electrical conduction from the source and the drain. So the N channel start to form. So the conductivity of channel is enhanced by increasing of the VGF. So we start from the zero VGS. At zero VGS, if we draw the graph of VDD, this is ID versus VDD. So VDD is application of voltage between drain and the source. Okay, when VGS is 0, so VGS is 0, so drain current is 0, because there is no induced channel. If we apply the VGS, if VGS is above the, I put this VGS1, above the VTH, threshold voltage, there will be a current flow. So we see this one as a resistor. So the current voltage characteristic will be a linear characteristic. We'll have the specific resistance here. So the current will flow, and the current will increase as we increase the VDD. So next, what if we apply the gate voltage that higher than the previous gate voltage? Let's say we put here is the VGS2. If the VGS2 is higher than VGS1? So what will happen? We will have the much lower resistance channel. So the drain current will be much higher than the case where we apply the VGS1. So this is the the explanation for the first statement. The conductivity of channel is enhanced by increasing the VGS. Okay. Okay, as VGS is increased beyond the VGSTH, ID will continue to increase. Okay, this is the ID versus VDD. So we get this characteristic ID versus VDD. Okay, and I would like to take note. Please take note that although in this slide we put a VDD here, in a more common expression is VDS, because here this is a drain. This is drain terminal, and this is a source terminal. So we put it a VDS as a symbol. Okay, so next, what happen if we apply much higher VDD or VDS? Much higher VDD and VDS. So in order to explain this phenomena, I would like to explain or describe the shape of the induced channel, the difference between the channel at the drain and between the source at the end, between the source end. So what I mean here is, let's say you are considering a capacitor here. So the voltage applied to the capacitor is a VGS, the gate voltage. Okay, and then the voltage at the bottom terminal of the capacitor is not fixed to the ground. So the value here depend on the location. For example, this is a source, this is a drain end. Okay, this is source, again this is source, and then this is drain. Okay, you see here the source is connected to the ground, so this is connected to the ground. How about the drain? The drain is connected to the VDD. Okay, the drain is connected to the VDD. So the effective voltage across the capacitor will be different at the point along the source and the drain. For example, the effective voltage applied to the capacitor at the source end is, because the source is grounded, so this is a VGS. But in the drain, let's say I put so in the drain, the voltage at effective voltage across the capacitor is VGS minus VDD, because we have the application of voltage here. So we see here the voltage at the drain end will be much smaller than the source end. So what will happen is the electron channel, or the electron accumulated at the drain end will be much smaller, and then the channel will become much thinner. So this is the explanation. If you draw the MOSFET, okay, this is the MOSFET. So if I want to draw the channel across this along the source and drain, this is the source and this is drain, this is gate. So the shape of the channel will be this is the electron channel. So you see here the channel, the thickness of the channel at the source end will be much thicker compared to the channel at the drain end. So as VDS increase, so this is the induced channel, the difference between at the drain end and the source end. Okay, so what happens if we increase the VDD here, or VDS? We call it VDS. If we increase the VDS here, the effective voltage at the drain end become much smaller, and then the channel become much thinner. Okay, at certain point, when we apply a VDS voltage higher at a certain voltage, there will be a phenomena, we call it a channel pinch off. So the channel will eventually reduce to the point of pinch off. So what is the pinch off? So the pinch off phenomena, this is the n-type source, this is the n-type drain. This is gate. Okay, the pinch off is where the channel at the drain end is reduced to the 0. So what happens if I draw the pinch off case or the pinch off situation? The channel will look something like this. This is the channel. So you see here, at this point, the accumulated electron is almost 0. So this is the pinch off. Means that there is no induced channel at the drain end. Okay. So what happened is, although there is no, although the channel is pinched off at the drain end, the current can still flow from the source and drain. But there will be a change in the IV characteristic. Okay, I have drawn the ID versus VDS. Okay, because at the small VDS, this channel along the source and drain function as a resistor, so it will have a linear characteristic. However, if it reach a voltage where the channel pinch off, so this pinch off operation will reduce or will restrict the further increment of the current, drain current. So what happen is current will start to saturate. So current will start to saturate. So this is ID saturation. So this saturation current is due to the channel pinch off. The saturation condition is established. Any further increase in VDS at a fixed value of VGS will not affect the saturation level of ID until breakdown occurs. So if we further increase the VDS, so the current will still fix at the VD saturation until it reach the breakdown condition. Okay. So the point where the current start to saturate is called VD saturation. Okay, VD saturation. So we know that the VGS need to be higher than the VT, right? In order to form the channel. So at the drain end, the VGS here is VGS minus VDS. So this need to be VTH. So at the pinch off condition, the relationship between the right side and the left side is equal. So the pinch off situation occurs when the VGS minus the VDS is equal to the VTH. So now the VDS here is called VD saturation. So VDS here is equal to VGS minus VTH. Okay. So this condition is where the VDS value where the pinch off start start to occur. So this is called a VD saturation.